Now that we know that two-dimensional problems, plane stress or plane strain problems, are governed by a smaller number of equations, 8 equations instead of 15, we can try to figure out ways of solving them. Okay, so one way of solving them is to solve in terms of what is known as the Airy stress function. So Airy stress function method is a method that we are going to learn now. Now imagine that there are body forces, and because I have put this Greek index alpha, which goes from 1 to 2, which shows that there are two body force components at each point, B1 and B2, and we assume that these are given in terms of a scalar potential. So uh, scalar potential V, which is a function of x1 and x2. So B1 and B2 are given in terms of a scalar potential. How the scalar potential will look like, we will see in a moment. B1 and B2 are specified, given in terms of, and they can be expressed in terms of a scalar potential. Then the idea of Airy is that the three relevant stress components are sigma 11, sigma 22, and sigma 12 for a plane stress or plane strain problem. For a plane strain problem, of course, sigma 33 is there, but that's not independent. So these are the only three independent components of stress in both plane stress and plane strain. And I introduce another scalar function, which is a function of x1 and x2, which we call the Airy stress function, so that sigma 11 is expressed as this, sigma 22 as this, and sigma 33 as this. These are second derivatives of phi with respect to x2 square, x1 square, and x1, x2 square. What is the advantage of doing this? The advantage of doing this is the following. Remember that we have two relevant equilibrium equations now. So they are del sigma 11 del x1 plus del sigma 12 del x2 plus b equal to b1 equal to 0, and del sigma 12 del x1 plus del sigma 22 del x2 plus b2 is equal to 0. Now if you take the first one, now you have del x1 del x1 of replace this with the expression in terms of Airy stress functions, del square phi del x2 square plus v plus del x2 of minus del square phi del x1 del x2 plus b1 is equal to 0, and this will give you del square phi del q phi del x1 del x2 square minus del q phi del x1 del x2 square, the order doesn't matter, plus del v del x1, and b is minus del v del x1, which means this cancels, and you have 0 equal to 0. So it means that you can do the same thing to the second equation as well. It means that if I make these, if I can express the stresses in terms of the Airy stress function, which I still don't know, but suppose there's a scalar function which in whose terms I can express the stresses, then these stresses are going to satisfy the equilibrium equations identically. So these are guaranteed to satisfy the equilibrium equations. So this is the great thing about the Airy stress function, that if you can find the Airy stress function and write the stresses in terms of it in the manner shown, then they are going to satisfy the equilibrium equation identically. So now the only compatibility equation in plane strain and plane stress is this. Out of the six, only this is valid, because the only non-zero components of strain are epsilon 1 1, epsilon 2 2, and epsilon 1 2. Epsilon 3 3 is there in the plane stress case, but it's not independent. So this is the only one that you need to satisfy. Now what I do is I convert this into an equation in terms of stress. The way I do it is I go back to the constitutive equation. So from, let me erase this. So I have sigma 1 1 equal to del square phi del x2 square plus v, sigma 2 2 equal to del square phi del x1 square plus v, and sigma 1 2 is minus del square phi del x1 del x2. So this is what I have assumed. And then I have the two-dimensional constitutive equation, which is sigma alpha beta equal to 2 mu epsilon alpha beta plus kappa epsilon r delta alpha beta. Now this is epsilon 1 1 plus epsilon 2 2. If I take these approximations and plug it into here, I have the stresses in terms of uh, I have uh, I plug it in this side, okay, and I have three of them. I can solve for the three strains in terms of the stresses. That's a bit of a tedious calculation. So I plug in the stresses, not along this route. This is wrong. Okay. So I plug in the stresses on the left hand side, and then I have epsilon 1 1 2 2 and 1 2 on the right hand side. I solve for epsilon 1 1 2 2 1 2 in terms of sigma 1 1 2 2 1 2, and then I put them back into this equation, taking care of the fact that kappa is different for plane strain and plane stress. So when I do that, I get this equation after a bit of a tedious calculation that I suggest that you go through. This is for plane strain and this is for plane stress. If there are no body forces, then this side is 0 and this side is 0, and there is no difference between the plane strain and plane stress equations. If there are body forces, however, then there is a difference because of the change in kappa from plane strain to plane stress. Okay, so once you have this, now you can replace these with their Airy stress function approximations. And when you do this, you get this for plane strain and this for plane stress, where del 4 phi is the same as del square of del square phi, and if you work this out, it turns out to be this equation. Again, if there are no body forces, in both cases del 4 phi is equal to 0. If there are body forces, then you have these slightly different equations on both sides. The equations differ only in this coefficient here, only in this coefficient here. So plane strain and plane stress problems can more or less be solved on the same footing. So we have reduced the problem of solving a plane stress or a plane strain situation to one of solving a what is known as a biharmonic equation. So this is the harmonic equation, and then another one gives you the biharmonic equation. So finding a function which is a solution to the biharmonic equation will give you the solution right away to the problem of plane stress or plane strain situation without body forces. With body forces, you will have to still solve the biharmonic equation, but with the right hand side not equal to 0. Now this is in some way a remarkable result because what we have done is we have started with an assumption on the stresses in such a way that when stresses are expressed in terms of the scalar potentials, these expressions automatically satisfy your equilibrium equation. Now we have then used the uh, compatibility equation, and uh, we have already used the equilibrium equation. Then we have used the compatibility equation to arrive at the biharmonic equation. So this biharmonic equation again is in terms of one scalar function of x1 and x2, that is phi. But if you find phi, you are guaranteed to satisfy both the compatibility as well as the strain displacement relations, as well as the equilibrium equations, and as well as the constitutive equations of linear isotropic elasticity. Where have we used the constitutive equation? We have used the constitutive equation in coming from this step to this step. There we converted the strains to the stresses. That's where we use the constitutive equations, and therefore the constitutive equations are also incorporated in the biharmonic equation. So the whole problem of finding the 8 variable stresses, strains, and displacements is now reduced to that of finding the Airy stress function. And once you have done that, as I said, in case of anti-plane shear as well, when you have done that, even by guessing, you have found the solution, because the solution to these problems is always guaranteed to be unique. Okay, so this is the framework that we are going to use at the beginning to solve um, solve problems in plane stress or plane strain. And first, I will show you situations where we do some kind of a brute force solution. So we just assume that phi is a very long series and then try to find the coefficients in the series. That's the brute force situation that we will utilize first. It works. It's not very clever, but it works. And then we will go on to show that more sophisticated techniques can somehow be used, in some cases can be used in order to solve problems which are governed by the biharmonic equation.